So I'd like to take a look at this method called image charge, the image charge method. We'll eventually just apply that to a particular problem, namely a point charge above a grounded conducting plane. The method of images is a method of replacing bounding surfaces of some space by appropriate image charges. The one important thing that it relies on is what's called the uniqueness theorem. So let's suppose you have a solution of Poisson's equation or Laplace's equation for a region of space, and it satisfies a given set of boundary conditions. So for example, suppose you have some conductors, and let's talk about Laplace's equation. So these are at potentials, and you have this space here and a solution of Laplace's equation in this region here. Okay, so you have a solution, and say it satisfies the boundary conditions. So this is V1 and this is V2, say. The conclusion of the uniqueness theorem is that this is unique. The solution is unique in the sense that if you had two solutions, they'd be equal to each other. Well, that's an important point, because if you look at a solution to either of these equations, if it satisfies the boundary conditions, then the solution is unique no matter how we obtained it. If you have a benevolent alien tell you what the solution is and it works, then you have the solution. The image charge method is a method of, I put into quotes, guessing the solution and then checking to see if the boundary conditions are satisfied. So you don't solve the equation by Laplace's equation or Poisson's equation. You do it by setting up image charges that satisfy the boundary conditions. More specifically, it's a method for solving problems where a charge or many charges are near a conductor, and actually it can also be used for charges near a dielectric, by finding analogous problems involving only point charges. You remove the conductor or the dielectric and replace it with point charges. We're going to start with the simplest case, and that is a single external point charge above a plane. Superposition enables you to generalize this case to many charges. So here's the problem. You have a system where the region below Z is occupied by a grounded plane, while for Z greater than 0 it's vacuum except for a point charge a distance d away from the plane. And we ground it in order to have a zero potential for the conductor. So here's our charge along the z-axis. The origin is right here. We're going to use an image charge. To find this potential and electric field, we're going to have the case, for example, that the solution below is trivial because E equals 0 in the conductor and V equals 0. And the reason it's 0 is because we've grounded it. In addition to the potential in the E field, we'd like to find the induced surface charge on the metal surface. And because you're at Z equals 0, this would be a function of x and y only. The metal, in a sense, screens the electric field from the interior of the conductor by inducing this surface charge on the surface. We'd like to find the total screening charge, or surface charge, and we'd like to find the force on Q due to the induced charge. And finally, we'd like to find the work done to bring this charge to its position from infinity. So, for example, you assume that you're at infinity, let's say along the z-axis, and you just bring the charge in from infinity to this position here. So what is the work done? Let's look at the boundary conditions. Here's our metal, which we have grounded. Here's our charge Q. Let's assume that's positive. The voltage for Z equals 0 along this interface must be 0 because of the grounded surface. The electric field at this interface has to come in perpendicular to the surface because this is a metal. So we have here the voltage for Z equals 0, 0. The electric field at Z equals 0 is normal. And then the next question is what direction it's in. Well, let's draw a typical streamline, so it might look something like that. It's coming in normal to the surface. This positive charge will induce a negative surface charge on the interface. And the reason is because the metal has to have 0 field. And so that negative charge will compensate for the positive charge and make the E field in here 0. So the E field will be in the negative Z direction. The magnitude of the E field will be given in terms of that surface charge density divided by epsilon naught. Now remember, this is a function of x and y, and so it has two dimensions. It's spread out onto this surface. Realize that surface would look something like that. Excuse me. And so we have surface charge density over the coordinates x and y. And as we've said before, that's negative. We will then show that our image charge solution satisfies Poisson's equation. And the reason we're going to use Poisson's equation is because there's a charge in the space that we're interested in. And Poisson's equation is familiar to you. So we satisfy this equation and the boundary conditions. If those two are satisfied, we then have a unique solution. And that's the one, of course, that we seek. So the big trick then is the image charge. So we're going to assume a negative charge placed at some z less than 0, which in combination with this charge here will produce above the plane the correct v that will satisfy the boundary conditions and satisfy Poisson's equation. So to save time, we'll ask an alien for the appropriate negative charge and its position. And the answer is that it's equal to just minus the charge that we put here, and the distance is equal in terms of magnitude to the distance to the charge. So I've shown that here. And the distance is from the surface. Now realize this could be a mile deep or it could be a thin sheet. It doesn't matter. So the metal can be thick or it can be thin. Minus q does not have to be in the metal. It doesn't have to be out of the metal. Either way is fine. Well, this is the diagram for generating the potential. And so you have these 2 point charges. And we'll use funny r minus for the distance between q minus and the field point. You could call this p if you wish. It's just x, y, z in terms of coordinates. And then r plus is the funny r from q to the point. And of course r is the position vector for the point p. And we know how to find these in terms of r minus r prime will give us these funny vectors. Going through that then, we can determine those just by simple triangle derivations. This quantity here, r plus, is given by the square root of x squared plus y squared plus z minus d squared. The type of triangle we're using is this one right here. And so this distance right here is z, the z coordinate, minus d. That will give you this change here. And so that's why we have z minus d right here. R minus would use a triangle. I'll try to draw it. It would be something like that. This triangle here. Now, this only holds for the positive part of the space. Require that v is 0 at the position z equals 0. And since it's either a infinite metal or an infinite sheet, then you'll have screening of the charge. If it's a metal, E has to be 0. If it's a sheet and you're in space, it has to be 0 because of the shielding that you would have if this were infinite. I just want to point out that in terms of the derivation that we have here, this is exactly the same as the original part of a dipole derivation before you make the approximations. And so you start with the same kind of thing. You have a dipole with two charges of opposite sign separated by some space. Here's the potential again, and later on we're going to show you what the plots of this potential look like. But I have to point out that you have a function of x, y, z over here, and then you have the independent function over here, which is a function of x, y, z. And you can't plot that in 3 dimensions because it's got 4 dimensions. So what we're going to do is the following. We're going to take this and cut it with a plane. So this is the plane that we're going to take. So we're going to set z equal to parameters, z1, z2, z3. So we're changing this in some way. That's taking a cut of this function and plotting that as a function of x, y. If we're down on the metal plane, we have 0. We've already suggested that this will go to 0. As we come up, we're coming closer to the positive charge, so we expect the potential to get more positive. And as a function of x, y, we expect the maximum right under the charge. Then if we come up here, and let's just pretend that that's in the plane of the charge, then the potential as a function of xy in this plane right here would blow up, because you'd have an infinity as you approach the charge. And then above, it'll still be a positive quantity, but you expect it to get smaller and smaller as you go above. So that's what we're going to be displaying. So let's take a look at the kinds of plots that I'm talking about. So here's our same setup. So I've given the equation. The first thing is that I want to see if at z equals 0 we actually get 0. We're going to do that by just simply setting z equal to 0. And here's our function, where this is just the part without the kq. So we'll just pretend those are equal to 1. I've set the kq equal to 1. I've actually just left it out. I'm going to set d equal to 2, and I'm going to say z equals 0. So what happens? We're going to plot that particular set of parameters, z equals 0, in 3D. So let me just do that. I'll run it again. You can see that it's right here. What you get is 0 everywhere. And I've blown this up so that you can see that if there's anything there, it's really small. And if you want to, you can add some more zeros, and it'll still look flat. And the reason, of course, is that really is 0, as you might expect. Okay, so now we look at v on different xy planes. And so as I've told you, if this were the plane now, we're going to look at this as cuts parallel to the plane as we increase z. To do that, here's our plot. This is what we're going to plot. And we're just going to plot the same space that I did here in x and y. But then I'm going to change z in a systematic way, and we'll see what that looks like. And here it is. We're at z equal to minus 3. You may not see it, but it's got a little dimple here. And so as I come toward the charge, so I'm coming towards the negative charge, which is at minus 2. So as I come towards that, yeah, there it is there, by the way. So you can see as we come towards the negative charge, then it really gets blowing up. And then as I go past it, then I get a finite value, almost. So let me just go a little further there. You can see we're going towards the plane. We're not there yet. The plane is at z equals 0. And so here we go. We go to z equals 0, and we're flat. And then when I go above the plane, I start approaching the positive charge. That's at z equal 2. So you can see as we go up, 1.4, we're getting close. We're going off scale. Let's change our scale. Let's make it 20. Okay, so again, come up. Come up. Okay, so you can see at 2, it goes off scale, and then as we go up, it gets smaller. So we're approaching the charge. Here's the charge. Now we're going away. And you can see that it just gets smaller and smaller as we go above the charge. So that's the way you can see what the potential is due to the presence of this charge as a function of z. And remember that z equals 0, you're in the plane. If you go down, you're getting in the region of this minus image charge. Then you go above, and then you have positive charge influencing this potential. Okay, now, here's the rule. Everything you saw below the plane was magic. You can't go down there. There's no potential down there. It's really just 0. So this plot going into the minus region might be interesting, and it certainly is true that there's some negative charge there in the problem, but it's not there in reality. Just keep that in mind. So the solution that we're really interested in is from here on up. Okay? So now let's take a look at the contour plots. The contour plots do the same thing. They do cuts through the potential and give you what this potential looks like as a function of z. D now is 0.14. I just happened to change it. I was playing with this before. So D equal 0.4, which would be right there. We have the maximum potential in the center here and nearby. And then if we go above, so we're above the charge, then you notice these numbers are a lot smaller. And in fact, if you go way out here, they get very small and far apart because you're getting the bump that is smaller. So this contour plot is this thing here. As you go up in z above the charge, then this will get smaller and smaller. So looking through sections of the potential at different values of z, we get contour plots of these functions. That's what this is. So now we'll find the E field by just taking the gradient of the potential. And we'll take a look first of all at the part where we just have the x, y, z dependent part, and we're just going to set those equal to 1. If you take that gradient, this is the result. So you can see that it's a vector. Here's the first component, the x component. Here's the y, and here's the z. Now these probably could be simplified better, but they're adequate. We could do a vector plot of this, but vector plots in Mathematica in 3D are kind of messy. So I'm just going to show you a streamline. And the way we do that is we set y equal to 0. We're going to set y equal to 0 up here. We'll be looking now in a cut in the xz plane. We're cutting through the origin. One coordinate is x and the other is z. We're going to set d equals 0.8. So here's the stream plot. The positive charge is right here. The plane is right here. So we're only plotting above the plane. So as you might expect, the field lines, remember this is a streamline plot of the electric field. The streamlines come out of the positive charge. There is E field above the charge, there is E field below, and notice here it all comes in normal to the surface, which it should because this is a conductor. The potential that gave us this field was exactly the one we got by putting the plus charge here and the minus charge below the plane. We are given a very pretty picture of what that field looks like in terms of the presence of the charge and the presence of the plane. Now this is a picture of what this should look like. This came from an old textbook of what the E field streamlines would look like in 3D. So it's this picture here where we take this plane. This would be just a cut through this diagram here. There's more field here. The density is high here, and out here is low. These streamlines are equally spaced, so it doesn't represent the intensity. Let's look at the charge density on that surface. We go back to our potential. So here's our potential right here. To find the charge density, we use one of our boundary conditions where we took the derivative of the potential with respect to the variable that's normal to the surface. And so in that case it's z. And we set that equal to minus sigma over epsilon naught, where sigma is the charge density on the surface, and we will take this derivative. Here's our kq out in front. This expression here is the derivative of the potential, the xyz part, with respect to z. And then we want to know what this is at z equals 0. You can't just set z equals 0, but you have to take the limit. This quantity here is the result of this step up here. So we take the limit of this, which is this. That's what this right here is. We take the limit of this as z approaches 0. So that will be then equal to minus sigma over epsilon naught. Well, once we get this quantity here, we can solve for sigma. So imagine that this equals this. Solve for sigma. You just multiply by epsilon 0 times the dv dz, and that's what this is right here. And the minus sign is this minus sign. This is the derivative, so this is the derivative of v with respect to z. That's all of this right here. Then we take the limit and we get this quantity right here. So that's the part of the equation that we have where we've taken this quantity and taken the limit down to z equals 0. Then we solve for the charge density by just taking minus that times epsilon 0, and here's the result. So I have then the charge density as a function of x and y. Now I can just call this the radial distance from the origin along the plane. And so when I do that then and set these equal to some simple numbers, including epsilon 0, then I can plot it. So I'm going to plot this function where all of this is equal to 1 and d equals 1. Doing that then I can plot it, and let's see what that looks like. And lo and behold, it's a fairly nice looking function. It is negative because the charge is negative on that surface. So the surface charge density is negative. Now if you don't like that, you can flip it over, and so you can see what it would look like in terms of magnitude. This is the density of that charge as a function of xy. And so this would be the induced surface charge due to the presence of that plus q above the surface right at the peak of this charge distribution. And one more time, it's negative. What is the total charge? Well, we can find that by just integration. And so I'm just going to replace x squared plus y squared with the distance r squared. And we'll just integrate our equation for sigma and rings of charge with an area element 2 pi r dr. So dq then, remember, is sigma ds. Notice here we have this ring which is at r dr, so the distance around is 2 pi r, and then times dr gives us this ds. I have the integral here. I'm going to set k equal to 1 over 4 pi epsilon naught, so that goes back as k. And I look at our equation then for the surface charge density here, and then here's our area element, and we integrate from 0 to infinity. This charge is negative, and so this negative sign should be there. Let's do that and see what we get, and we get minus q. So the total charge, the area under this curve, is equal to minus q. So the plus q induces a total charge of minus q. In this particular geometry, the image charge has the same value as the charge. That is not always the case, but in this case it is. This is the proof that we get zero potential at z equals 0, and that's quite easy because you'll have this part here and this part here when we set z equal to 0, so we're in the plane. Remember, this is the xyz part of the potential. Then they're equal because this is what we get, and so this equals this. With the minus sign we get 0. So every point in that plane, every x and y, we get 0. And so that's the boundary condition then that's satisfied for that potential that we derived.